Hello, welcome to this session on solutions of the first internal examination that was held a month back in our accelerated computing course. So let us see maybe first 5 questions in part A, which are for 2 marks. Give the 5 stages of instruction execution with a short one-line description on each stage. It's a pipeline stages and picture was not required in this question. Now let us talk about the different pipeline stages that we normally have in a processor. So we have read about the pipeline pretty much in depth in the subsequent classes, but this question is about just an introduction. As you are aware, there are 5 stages in a pipeline. First, you know that it is accessing instructions from instruction memory. So inside this instruction memory, which is called instruction fetch stage. And then the second stage will be to decode the instruction, understand what is it supposed to do. And once the instruction is decoded and the type of instruction and the operands are understood, operands are also accessed in this stage. Which are operands? They are like inputs to the instruction, which is read from the register set, which is there in the processor. Now, that is all this information which is being understood or processed in each stage is being processed through passed through a pipeline. But for this question, you don't need to give all the information, but I am just giving for a continuity sake because we are discussing about instruction pipeline. Please, based on the amount of marks that you are to score and the time available, try to give the summary at a high level. Don't need to go to the details of everything that is being explained here. Now, as you know that the pipeline is meant for taking in instruction every clock cycle, okay, and on an average, then pass on that particular information that you understand about the instruction to the next stage through pipeline register, and then it takes the next instruction immediately in the next clock cycle. That means what? The program counter, which is pointing at the instruction memory, needs to be incremented to the next instruction so that it is ready to access the next instruction in the next cycle. That means what? The incrementing of this PC, if suppose this is an address 100, to be equal to the width of the instruction, because that many bytes you need to access always. And remember that the addresses are pointing to a byte and we need to increment it by that many number of bytes based on the instruction width that you are reading from. It could be 4-byte instruction or 2-byte instructions, based on the mode of the processor. As you are aware, ARM has a thumb mode or the ARM mode, wherein you access different bytes of instruction. So assume that we have a 4-byte instruction width, then this PC is also incremented here apart from accessing the instruction. Now, I just want to give you another information that when we are saying instruction memory, do not assume that the CPU is always accessing from the instruction memory or a data memory, because you know that there are split caches available for code and data, which is L1 cache very close to the CPU. So, and then you have L2 cache, maybe unified or maybe split, and then you have L3 cache also. Then only the actual memory that we are talking about is coming here, main memory. But here always we say instruction memory because originally the data or a code which is residing in the memory is being read by the CPU. But in reality, it may be accessing it most of the time based on the hit ratio, because the instructions are being accessed and it will be found in the cache and it will be from the cache. So you can as well assume that this instruction memory access could happen within a clock cycle. Okay. Okay, clock cycle is here, one high and one low. Okay. So this is only to give you overview of instruction memory or instruction fetch that is happening in the first stage. Then decode is happening, wherein the instruction is understood and the operands are read. And as you know, the registers are being read only in this stage. It needs to be passed. The values are to be passed through the pipeline register, and it comes here, and we have a ALU which is operating on those operands which are being processed. It could be that it is adding the address with the offset, or it could be that the instruction says that you perform a arithmetic or logical operation that is performed by the ALU here on the operands that are being passed to it through the pipeline register. And the result is passed again to the pipeline register to the next stage, which happens to be a memory stage. Here we are talking about a data memory, wherein if your instruction is a load or store, then we will be accessing the memory. And as you are aware, load is with respect to the CPU always, and store is also with respect to the CPU. Store means the CPU is storing something into the memory. So then you will be, you can easily understand that CPU is trying to write into the memory some content of a register, which is a store operation, because all the operations are performed by the CPU with the registers in it, and the results have to be stored back to the main memory so that when the results are required later on, it is available in the main memory. So they are stored. So when the store instruction happens, memory write happens, and the memory write happens in this stage. If it is a load instruction, that means it is loading some value from the memory into the register. It will be a memory read, and it is reading from the memory into the register. So this needs to be understood clearly. And if the instruction is only a ALU operation, then there is nothing done performed in the data memory, and whatever results are passed from the ALU is passed on to the pipeline register of the next stage. Now the last stage of the pipeline is write back. That means it is writing back whatever results it has received from the ALU or from the memory. Maybe if it is a load instruction, it would have got some data from the memory which is available here, and it is passed on to the pipeline register, which is written back into the register, which is there in one place in the CPU. So this is about the 5 stages of pipeline. I hope this understood. The entire pipeline is understood. Now let us talk about the next question, which is about a generic. You know that there are processes are classified by Flynn's taxonomy, right? And there are different types of them: SIMD, SISD. I'm not writing in the same order. MIMD and MISD. And what does that mean? Single instruction, multiple data, single instruction, single data, and multiple instruction, multiple data, and multiple instruction, single data. So now I'm just giving a scenario where different documents. Okay, let us see what happens in a passport office. Different customers come with their own documents. Okay, we can consider them as a data. Okay, it is each person applicant is having different data of his own or her own personal data, which is maybe an Aadhaar card or a birth certificate, or it could be qualification of that person individual. So all this data is coming. People are coming with that kind of data, and we are providing passport office has given some instruction to the members who are validating them. So let me call them as member 1, member 2, and member 3, who have been given instruction. Each of them are given some same instruction, that if the first stage, now let us assume that one person is only sitting there instead of multiple person, then you may have a different scenarios. And if you see that every individual is given the same set of instruction, that you need to see whether the person name and the date of birth and everything is valid, all the documents that person is providing, the names are given properly or not, and cross verify those documents to verify there are any discrepancies in the document. So these are the instructions given to the individual. Now instructions are the same. Okay, we could interpret it this way. Okay, the same instruction. Okay, single instruction. Single instruction doesn't mean you give one instruction. It is a stream of single instruction. Okay, there may be different things need to be done by the individual, but the same stream of instructions are given. The person who is going through the document is going to apply the same set of instructions on those set of document that the person is providing. So, but once one individual goes and the other individual comes, you are going to look at the next set of data. Okay, but he is going to apply the same logic which is given to the person, right? the steps which are given to. So it is like a program wherein a single instruction stream is given to this individual and multiple data is fed to them, because he's not going to be the person sitting in the counter is not going to validate one person's data only. It's a multiple applicants are coming into the passport office, and you need to apply the same logic. So it is a SIMD which is to be given as an example and explain it in a crisp form. I'm explaining it in a longer way so that you understand the concept, but you can represent the same or give the same answer in a crisp with a couple of lines of answer. Okay, so this talks about the second question, which is SIMD. But if you have a valid explanation for MIMD, that can also be considered for the answer. Now, this question is little interesting, which actually understands or gives you, no, validates your understanding of the cache. Okay, see, the program is running in the CPU, basically the software which is being written by us, and the caches are of course sitting in between the main memory. Now, as you are aware, the data or the code or maybe a stack which is also having data of local variables are residing in the main memory. They all, based on whether code is read, it will be mapped to the instruction cache, and if it is data which is being read, it will be mapped to the data cache. It doesn't matter whether it's a global or static variable or a local variable. They all reside in a different locations of the main memory, and they have been mapped to the caches based on what the CPU is accessing at that time. Now, as you are aware, cache is having different policies. Now, what are those policies and how to understand them? There is a write allocate or read allocate. Okay, write allocate or read allocate. What does it mean? The processor may be doing something to do with the data. Okay, when I say write and read allocate, you should remember that it is actually referring to the data cache, because there is no writing operation performed with the data code memory. So code instruction cache does not have any writing operation to be performed, but write allocate is valid for data cache. And what does it mean? You are trying to write into a variable which initiates the write operation, and that write operation is of course referring to some data cache, data memory, either it is a stack or a data. Now, when you have this write access happening, there is a possibility that the cache is configured not to provide or no read a block of data from the data area into the cache. That means what? If you are performing 1 byte write, okay, you are writing into a 1 byte of data, you don't have to bring the entire block of uh, data from the memory to the cache. Okay, it is brought here, block of data. So it may be writing it directly to the data memory. That means it is a read allocate cache. If it is a write allocate cache, even for writing operation, okay, writing actually implicitly means that it is reading. Okay, so it actually differentiate between the first operation that you perform, whether you are performing a read operation or a write operation for a particular data in a cache which may be mapped to a new block. Then what is the cache performing? Whether is it going to get the entire block of uh, data from the main memory around the byte or a word the CPU is trying to access. Always remember the block size is a little bigger compared to what the processor is trying to access within the block. So you can understand that if it is a write allocation, any write operation performed by the CPU is going to allocate a block into the cache. Now that is understood. Now let us understand what is that we mean by the allocation. When you are reading the from the data memory, you need to allocate it. So let me take a new place. So when you have a cache, we have a block of different blocks. No, let us assume that I cannot assume that there are odd number of blocks here. So let me draw 1, 2, 3, 4. I have drawn 5. So let me make sure that I always 6, 7, 8. So 8 blocks are there. Okay, 0 to 7. Now the block size could be 32 bytes, okay, or it could be 64 bytes, or for our simple arithmetic, we may say even 4 bytes, which is not, actually makes sense to have a cache of 4 bytes block size, but for our calculation, we can always make it smaller. So the main memory, what is happening? The main memory is also equally divided by the block, okay? The block size, okay? But you may have a page which is again in powers of 2 normally. You know that block size is always powers of 2, some 2 power x, and the page size is also a block of 2, no, sorry, multiples of 2. So you can even subdivide them into blocks. And again, no, L1 cache may have a smaller block size, whereas L2 cache may have a, I'm showing it small, but it block size will be larger. Again, that is powers of 2. So remember them always that we always access it in terms of powers of 2, because the address, whatever the CPU generating, is a binary address, and you know that each bit is corresponding to 2 to the power of 2 power 0, 1, 2, like this. So you can divide, partition these things equally, properly in the border, okay? Boundaries will be well defined, and you can extract out the address bits based on the block size or the individual cache size, okay? So once you know this block size is powers of 2, remember the cache size is nothing but multiples of block size, right? And that cache size is also powers of 2. It's not that you have 5 blocks inside a cache, okay? That's why I took care of 1, 2, 3, 4, 5, 6, 7, 8. It is 2 to the power 3. And the block size, if I am saying that it is 4 bytes, then it is 2 to the power 2, okay? So everything is in powers of 2. Now, the question here was, it's not about cache, which I am explaining so much. It is a simpler thing, you can easily understand it. Now, array, my array, I have declared, just given it, it most likely it will be inside a function. Then this array is a local variable, because I have not mentioned any stack. So it may be living in stack area. That doesn't matter for us. And the size I have given as 16, again to make that some even number is given. It is residing in somewhere in main memory, okay? Maybe stack segment is here and it is there, okay? Now, what are we doing? We are saying for loop and I less than the size, right? It is actually accessing the entire array, and it is a character array. So byte by byte, it is accessing it. But as I told you, CPU will be saying that I want to access it as a byte. But what is it accessing it for? First time it is accessing it, the my array of 0 equal to ch. That means it is accessing ch also, which may be residing in some memory close to the array, because it is all declared together, so that the linker will be keeping all those variables which are declared together in the stack, or no, it is allocated on the stack one after the other. So they'll all be in the contiguous memory space, and it is accessing ch and writing into the array. Now this array is accessed in a loop, so there is a temporal locality of reference, because one for loop is over, next for loop is going to access the next location. Again, it is also showing that there is a temporal as well as spatial locality, because the arrays are contiguous, 0 element and 1 element, 2 elements. So spatially also it is showing the coherence, locality of reference, as well as temporal loop is there because of for loop. So both locality of reference is there. So you know that this cache is, the array elements are stored in the memory in a contiguous space. So when you are accessing it, you are for a write purpose. Since the cache is of write allocation policy, it is going to access the key, allocate the blocks. Now, before we calculate the block size and the cache size and all that, remember there is one more thing which is said, fully associative. Okay, what does it mean, fully associative? Let me say, fully associative is, let me go down. There may be cache, we are talking about data cache, and I'm not showing, even number of blocks here or multiples of 2. Fully associative means whatever the CPU is trying to read, whichever block of the main memory, it will find a space in the cache, okay, because it is required immediately. So it will remove some block and then allocate it. And suppose your array size is 16, and we calculate that block size is whatever it is, we'll see 4 bytes, it is block size. So you can see that Okay. How do you find the cache size? Okay, it is already given 128 bytes of cache size, so very easy. You are not required to find anything, and 4 bytes of block size. So that means about 128 by 5, there's sufficient number of blocks there in the cache, and then it is fully associative. So you don't need to worry about whether am I mapping to the same location that I need to evict it. Okay, so it is going to be finding a free locations out of all the available blocks in the cache. So every 4 byte of access of this array, the for loop is going from 0 to 16, but 0 to 3 will be accessing the first 4 bytes, and then next element 4 to 7 will be accessing the next block of data. So it will be bringing every access as the for loop is going through, and it will allocate a new block in the fully associative cache. And it is a right allocation, so it will, for every access in the for loop, it is going to allocate a new block in the cache. So how many it will allocate? 4 into 4, 16. So it will be having 4 blocks allocated on the cache. Okay, that's what you have to say when it says that above program is executed. How many cache line and block are same? So I am using both to make you aware that they are same, and cache lines are same as blocks, so will be used by the program. Okay, inside the my array. After that, my array is gone and they may be evicted. That is not our problem. But I am showing you a piece of code and then asking you how many blocks are used, and for sure it will be using 4 because my array access, with respect to my array access only. I am not talking about ch may be residing and it will be using that another block for it to be brought into the cache, but I am taking accessing with respect to the my array, it will be 4. And will the dirty bit of those blocks be set? See, remember, after accessing the block from the main memory and bringing it to the cache, write operation is happening. Okay, ch is written, ch value is incrementing, so new value of 0 1 2 3 4 or 1 2 3 4 5 will be written into the cache, and remember that will be writing into the cache, because every write operation I am not going to go to the cache, sorry, main memory, because write allocate means I am bringing a cache block of data from the main memory to the cache, and then any write operation I perform on it, I am doing it in a local copy, because there is no fun in writing it back to the main memory every time. As long as the write through policy is not given, we will not be doing a write allocate and then write through policy, because which is not helping each other, and it will be a write back which will be done when the block is getting evicted. So every time it will be written into the block in the cache. So dirty bit is the one which is showing that a particular cache block is modified or not. So because it is writing the data which has been generated by this program, now ch is incremented every time and it is generating some new data to be written to the main memory, but locally it is written into the cache. Later on it will be written when the cache block is evicted. So the answer is write blocks of all the blocks which are being brought into the cache will be modified, or it will be set. Okay, that's the answer. I hope it is clear. Now let us go into the next question. What is it? It is about the again cache, because we are concentrating more on cache here. Remember, the CPU is accessing the cache. Let me show only one cache here for a simplicity purpose. It doesn't matter with the data instruction cache. What happens is CPU is generating the address, because the program decides which access needs to be performed and which address the access has to be performed. So the CPU is generating the address. Now, the immediate thing what the CPU does is whether that address is, the content of that address is available in the cache or not. Okay, and if it is available, it is taken from the cache and given to the CPU. Okay, it may be because of load or store or any stack operation, push or pop, and it is providing the data if it is available in the cache. So that is called hit. That means the access time of the cache, either physical or logical cache, is much lower than the main memory access. So let me call that as a TC, time taken to access the cache, and that is for a particular access. And if I have a 200 access in total, if it is happening as per this program question what is given, then I have to multiply the time taken for one access into 200. Okay, I have to multiply that. Now let me understand, is it a hit or a miss? Now, which will be more? Now, normally the miss rate is supposed to be low than the hit rate. Okay, That is why we have a cache in the system. And I say that miss rate is 20. I could say hit rate is 80, or maybe hit rate is 70 and miss rate is 30, or one of them can be mentioned. Okay, will be mentioned because it is a percentage business. So if it is hit rate is given as 80%, then it is a zero point 0.8 times it is accessing the cache from the cache, and the miss rate is 0.2. The rest of the time is going to be accessing the from the main memory. Now, always cache, we will write it with a hit rate. Okay, let me just write say hit rate. Let us expand it later on. Plus, how much is the miss rate? Miss rate you will calculate it based on whatever the number given. In our case, it is 0.2. But what is the time taken for one particular access? If it is a miss, what happens is it will be found out before even accessing the cache. Remember, the address is resolved using the extracting out the block number, and then it will mapping based on whether fully associative or direct mapping. It is finding out that whether the available address, the content of that address is available in the cache or not. So it will not be accessing the cache. Now, before that, it will find out that there is a miss. It will generate that particular address to the main memory, or maybe the second level of cache. But in our case, we are assuming that there is only a single level of cache, and the rest of the accesses go to the main memory. So it is going to access the memory. Now, once the data entire block is brought into the cache, okay, always remember we are not going to bring only one byte. Even though the CPU is interested in one byte, the entire block is brought. So the CPU is not stopped. The instruction is not going to be no executing, and it is going to take some time for the block to be coming from the main memory. We remember it is not an easy job because you need to find out whether there is a free block available in the cache or not. Otherwise, you have to evict that particular block. If that evicted block to be evicted is having the dirty bit set, then you have to write back that particular block into the main memory. Now, writing a block of cache data is not a small job. It takes some time, and then bringing another new block which is required to be into the cache. So it all happens, and it takes sufficient time, which is a memory access time. Then it is read from the cache. So it is always TC plus TM for accessing a missed data into the CPU. So miss into TC plus TM and hit into TC into the number of accesses will be the total access time. So you have to calculate the total access time with respect to the cache. If it is the cache is there, if there is no cache at all, every access is going to be memory. So you will be now accessing all the 200 instructions using TM. So calculate that as a total access time. Okay, with respect to the whether cache is there or not. Which, if you perform this based on the numbers given, you will see that there are 8,000 nanosecond it will take without cache, and then 2000 nanosecond it would take with the cache. Okay, I want you to perform this simple arithmetic, and then the time saved will be 8000 or 8 minus 2 in terms of microsecond. So 6 microsecond will be the answer. Okay, I hope this will be easy to calculate, and let us move on to the next question based on the time available. Now let me stop with this fifth question in this recording. What are the logical cache and physical cache? So MMU is sitting always, you know that between main memory and the CPU, there is a MMU there. Now the cache can be either be located here before MMU or after MMU. If your cache is here, it is called logical, because logical addresses are generated always by the CPU. So a cache which is sitting not kept in between the CPU and MMU is called a logical cache, and if the cache is located after the MMU translation, it is called physical cache. Now, to understand this, you little bit of you have to bring in your understanding of main memory and the logical physical related to the OS, what we learned in the OS course. So you know that memory is there sitting to translate the virtual addresses to physical addresses, right? So how is it done? There is a page table which is there, no, because always the OS is going to be accessing with respect to the pages, and different pages are accessed, and the translation is kept in the page table so that you will always be able to understand the MMU's translation and what exactly then which virtual address is mapped to which physical address, right? Now, before we understand the physical and logical address, remember the logical addresses are decided by the tool, maybe a linker tool, which is deciding that, okay, my code area will be in my logical address of the so and so, and my data area will be a logical address of something, right? If you are using the same GCC compiler, or maybe you may use a VC, a different tool or IDE, different IDE, then they will be using different compiler. So based on the compiler that you use to generate the executable, they all by behaving in the same way, and then they may be generating their logical addresses or mapping those your program's data code into particular logical addresses that it thinks, it has been programmed to generate them. Now imagine you are using always GCC on your system side and the OS side, where the machine, then you have built different executables using the same compiler GCC, right? And it would have all mapped the program to the same addresses. Okay, main code maybe first code it will be from 10,000 hex or 20,000 hex for data, something like that. The tool would have decided it. So when you have such mapping for all the programs that you are using it in your executable, you are using it in the CPU, and you know that different processes are running and they are brought into the main memory by the OS. Now, remember, you have enough physical memory to accommodate different programs to be brought into the main memory. Okay, so you may have program 1 here, program 2 maybe here, in the program 3 may be residing in the different parts of the physical memory. So you have to have this understanding that at the same time, different processes will be residing in the main memory. It's not that we are going to go to the hard disk for every access, but as the program progresses, you may have to have a page fault, and page itself will be missing, and you need to bring the pages to the main memory. So that is more rare. It is not going to be very frequent, but for our maximum amount of time, you will be accessing it from the cache and the page residing in the main memory. Okay, most of the time page faults are not very frequent. So in that case, what is logical to have a logical cache or physical cache? If you have to understand this much of understanding background is required. I want you to know. It is not that only to answer this 2 marks question, but it is to have a holistic view of how things work, so that in an interview, when you are asked questions and the interviewer is going to go deeper into multiple questions, wherein you will be able to support your answer with as much of depth as you can, you can go in. So now what happens? Your program is running in a physical scenario, scheduler is coming into play, and then P1 is running for a while, and then P1 is waiting for some data to happen, or maybe some IO has been created, initiated. So it has to be context switch has to happen, and the new process will be brought in. Now, imagine a situation wherein two processes are running, and they are maybe performing a no context switch between each of them in the CPU based on what operation they are performing. You can assume that the P1 pages and P2 pages, whatever is required for the processes, are all brought into the main memory. They will all be residing in the main memory. And imagine they may be using a library. Most of the time, printf will be used. So our stdio or whatever library is there, they're also brought in. Okay, you have to remember that shared library that we learned in the OS course, wherein the same library of C is used by all the processes, shared memory, and that is residing in our particular physical location in the main memory. So if you have all this in your back of the mind, then the answering this question is easier, because what is happening is, if you are using logical cache, what happens is, since all the GCC compiler is going to map all the processes to the same location in the virtual address, and if you are using logical cache, the virtual addresses are mapped to the cache, and the same locations most of the time may be mapped to the same different processes. So when you have a logical addresses being generated by the processors, you may have to evict because there will be a more cache misses happening and you may have to evict the cache. So that is the problem with the having a logical cache because it is mapping all the logical addresses to the different blocks of the caches. But if you assume the physical addresses are used and you have a sufficient cache size, then different caches, different part of the physical memory belonging to P1, P2, P3 are mapped to the different blocks of the cache. So when the context switch happens, most likely that you are using locality of reference is helping you. You are using different parts of the physical memory of different processes mapped to different parts of the cache. So the misses of happening, the probability of miss happening with the physical cache is most unlikely because you have sufficient cache size and then they are mapped, maybe P1 related blocks are here, P2's related caches, blocks are here, maybe P3 related process P3 related cache, blocks are here. So when the MMU sitting here, though there is a possibility that the cache is every address is translated, virtual address is translated to physical address, and it is being mapped to the physical cache here. It is not going to be more frequent because you know that there is a TLB, which is translation look-aside buffer, having the translation of this MMU business available in its own TLB cache. So even if the MMU translation is not going to happen more frequently because it is going to be looking into the TLB instead of going to the MMU and then getting the not address translated. So more frequently TLB is going to have a hit. So you can ignore the time taken by the MMU coming into the our discussion. So the advantages of having a physical cache, that is what is being asked here, is that it is going to be mapping different physical memory. Each process is residing in different parts of the cache, part of the main memory, and which is not shown here. And they are going to be mapped to different part of the cache. So it is going to be having a lot of hits only, not the misses. Okay, so that's one advantage. Another advantage is library, which is shared library is residing in different part of the physical memory, and that will be taking a different part of the cache. So you will not have even if there is a context switch, you may not have too many misses, and because they are using the standard library, they will all be residing in different parts of the physical memory and they are mapped to different part of the cache blocks. They will also be helping each other in terms of having physical caches. That's why in a recent processes you will feel that physical caches are used for a better performance in the recent CPUs. So this is the a total summary of entire gamut of how the virtual addresses, the OS and TLBs and all of them sit together, and they are all being discussed here for your holistic view, not for answering this 2 marks question. Please understand, bring out only the key points, what is being discussed at the end of our discussion, that the physical cache helps in terms of um, a lot of missed hits happening because of physical memory of different processes or different locations, and they will be mapped to different parts of the cache blocks. And the library shared libraries are residing in the different parts of the physical memory, which is also mapped to different parts of the, most likely to map to different parts of the cache, and it is also going to help us in terms of having physical caches in the system. Okay, with that, let me end this session and let us discuss about the remaining part of the questions later. Bye.